Welcome to The Explainer. All right, today we're diving into two revolutionary technologies that are just completely rewriting the rules of speed and space. On one side, you have the patient, relentless push of ion thrusters, and on the other, the blistering, atmospheric fury of scramjets. It's a classic tale, the tortoise and the hare, each racing towards a totally different future. So let's just get one thing straight right from the get-go. We are looking at two radically different solutions because they're solving two radically different problems. For deep space, the challenge isn't about raw power, it's about endurance. It's a marathon where being efficient with your fuel is absolutely everything. But for hypersonic flight, right here in our atmosphere, that is an all-out sprint. The goal is just to get from point A to point B faster than anything ever has before.
To really get why these new engines are such a big deal, you gotta look at what we've been using. For more than half a century, we've relied on chemical rockets and your standard jet engines. They're powerful, sure, and they've been proven time and time again, but they're hitting some fundamental limits, both in how efficient they can be and how fast they can go. To push beyond that, we have to move past controlled explosions and really start thinking differently.
Okay, first up, let's talk about our tortoise in this race, the ion thruster. And hey, don't let that whole slow and steady thing fool you. This technology is exactly what makes long-term exploration of our solar system actually possible.
So, instead of a big, messy chemical explosion, an ion thruster is all about elegant physics. First, you take a gas, usually something like xenon, and you zap it to strip away electrons. This creates positively charged particles, or ions. Then, and this is the really cool part, a powerful electric field grabs these ions and flings them out the back at incredible speeds. We're talking tens of kilometers per second. As they shoot out, they create this gentle but constant push. And finally, a little neutralizer shoots electrons back into the beam, just to make sure the spacecraft itself doesn't build up a weird electrical charge.
Okay, so how do you even measure how good one of these engines is? Well, the key number is something called specific impulse, or I subsp. The easiest way to think about it is like a car's miles per gallon rating, but for rockets. It just tells you how much oomph you get for a certain amount of fuel. The higher that number, the more efficient the engine is. Simple as that.
And this is where your jaw kinda hits the floor. A typical chemical rocket, the big fiery ones, might have a specific impulse around 450 seconds. An ion thruster? It can hit 10,000 seconds, maybe even more. That's over 20 times more efficient. It means a spacecraft can go so much farther with the same amount of fuel. It's not even a fair fight, it's a total game changer.
But, and this is a huge but, here's the trade-off. All that amazing efficiency comes at the cost of raw power. The actual force an ion thruster produces is incredibly tiny. We're talking about the same amount of pressure you'd feel from a single sheet of paper resting on your hand. Now, out in the vacuum of space, that tiny constant push adds up over months and years to achieve insane speeds. But you can see why it's completely useless for, trying to lift off from Earth.
And look, this isn't just some sci-fi concept on a whiteboard. This stuff is real. NASA's Deep Space One mission was the trailblazer. It proved these engines could just keep on running for thousands of hours. And more recently, the Dawn mission used its ion engines to become the first spacecraft ever to orbit two different bodies in our solar system, the asteroid Vesta and the dwarf planet Ceres. A mission like that would have been flat out impossible with a chemical rocket. It just wouldn't have had enough fuel.
Okay, enough of that slow and steady stuff. Let's switch gears completely and talk about the hare in this story, the scramjet. This is an engine built for one thing and one thing only. Pure, unimaginable speed inside our atmosphere, operating right on the ragged edge of what is physically possible.
Scramjet. It stands for supersonic combustion ramjet. Now, a normal jet engine, or even a simpler ramjet, has to slow the air coming into it down to subsonic speeds before it can burn any fuel. But a scramjet does something that sounds like it breaks the laws of physics. It injects fuel and keeps a fire lit inside an airflow that is already moving faster than the speed of sound.
On paper, it sounds almost easy, right? You've got an inlet that scoops up the hypersonic air using the vehicle's own speed to compress it. Then, in the combustor, fuel is shot in and has to ignite and burn in just a few milliseconds. And finally, a nozzle expands all those super hot gases to create enormous thrust. The catch? Every single one of those steps is just fantastically, mind-bogglingly difficult.
Yeah, so how on earth do you solve that problem? The best way to think about it is to ask yourself this question. Trying to keep a stable flame going inside a supersonic airflow is exactly like trying to light a match and keep it lit in the middle of a hurricane. The air is just moving so ridiculously fast that the flame has almost no time to catch.
But here's the thing. As crazy as it sounds, it works. We've seen these massive breakthroughs. NASA's X-43A aircraft hit speeds of over Mach 9.6. That's nearly 7,000 miles per hour. That's fast enough to get you from New York to LA in about 20 minutes. It proved that scramjets are viable, and ongoing programs like HiFire are gathering all the data we need for a future filled with hypersonic aircraft and maybe even reusable spaceplanes.
So, you've got this super slow, super efficient engine for space, and this ridiculously fast engine for the atmosphere. They're polar opposites, right? Well, what if I told you they share a secret weapon? Because both of them are completely dependent on an unseen pilot, artificial intelligence.
But you gotta understand, the AI is playing two totally different games here. For the Ion Thruster, the tortoise, AI is like a grand chess master. It's planning optimal routes that take years, carefully managing engine health, and making sure not a single gram of precious fuel is wasted. For the scramjet, the hare, AI is more like a fighter pilot with superhuman reflexes. It's making tiny adjustments to fuel flow in milliseconds, all to prevent a catastrophic failure called an unstart, where the whole engine basically backfires violently, which can rip the vehicle apart in an instant.
Okay, so let's zoom out. Why should you care about any of this? What's the end game here? Well, it's because these technologies represent two very distinct paths to completely redefining what we're capable of, both out in space and right here on Earth.
Our tortoise, the Ion Thruster, it's literally the key to unlocking the rest of our solar system. It enables these long, sustained missions that make exploring the asteroid belt or the moons of Jupiter not just some one-off fantasy, but a practical, doable reality. It's the engine that will power scientific discovery for decades to come. In the hare, the scramjet, it's about to make our planet feel a whole lot smaller. I mean, just imagine. An aircraft that can get you to any point on the globe in just a couple of hours. This doesn't just change commercial travel. It totally revolutionizes military response time, intelligence gathering, the whole shebang.
And this is where things get, well, really serious. The strategic implications are huge, and you just can't ignore them. In space, ion thrusters allow a nation to have a persistent presence, to keep eyes anywhere, indefinitely. In our atmosphere, scramjets mean no point on Earth is safe from reach for more than a few hours, which completely upends global military strategy. Mastering either of these technologies doesn't just give you an edge, it rewrites the fundamental rules of global power.
So that kind of leaves us with this massive question, doesn't it? The tortoise is pushing us, patiently, towards new worlds, while the hare is racing to give us total dominion over this one. As these technologies mature and become more common, the real question isn't just about what they can do, but what we'll choose to do with them. Are we going to reach for the stars, or are we going to tighten our grip on Earth?